Large language models do not read text the way humans do. When you look at a sentence, you see words, meanings, grammar, and context. A language model sees numbers. The bridge between human-readable text and machine-processable numbers is tokenization. If you understand tokenization deeply, you understand the true front door of every modern language model. At a high level, tokenization is the process of breaking raw text into smaller pieces called tokens, and then mapping those tokens to numerical IDs. These IDs are what the model actually consumes. Everything the model knows about language flows through this bottleneck. If the tokenizer behaves oddly, the model's behavior will also appear odd, because the model can only reason over the token sequence it receives. It is tempting to think tokens are simply words, but that assumption breaks down almost immediately. In most modern language models, tokens are not full words. They are often subword units, fragments of words, complete short words, punctuation marks, or even whitespace patterns. The reason is efficiency and flexibility. If we force the vocabulary to contain every possible word in every language, the vocabulary would become impossibly large and the model would struggle with rare or unseen words. Subword tokenization solves this by decomposing language into reusable building blocks. Imagine the word unbelievable. A tokenizer might split this into believe, and able. This allows the model to generalize to words it has never seen before, such as unbelievableness, because the pieces are already familiar. The model doesn't memorize every word, it learns patterns over token sequences. To understand why tokenization matters so much, consider the basic data flow of a language model. Raw text enters the system. The tokenizer converts text into tokens. Each token becomes an integer ID. Those IDs are mapped into vectors through an embedding table. Only then does the neural network begin its work. If the tokenizer makes a poor segmentation choice, the downstream representation is already distorted. In other words, tokenization is not just pre-processing, it is part of the model's effective architecture. There are several major families of tokenization algorithms. Historically, the simplest approach was character-level tokenization. In this scheme, every character becomes a token. This has the advantage of simplicity and complete coverage. Any string can be represented without an unknown token. However, it has major downsides. Sequences become very long, which increases computational cost. Also, the model must learn longer range dependencies to reconstruct meaning from characters, which is inefficient. At the other extreme is word-level tokenization, where each distinct word is its own token. This was popular in early natural language processing systems. The benefit is that sequences are shorter and align with human intuition. The problem is vocabulary explosion. Languages have huge numbers of possible words, especially when you include inflections, compounds, and domain-specific terminology. Rare words become unknown tokens, which harms performance. Modern large language models typically use subword tokenization, which sits between characters and full words. The most common algorithms include byte pair encoding, word piece, and anagram language model tokenization. Each uses a different method to build a vocabulary of frequently occurring text fragments. Byte pair encoding, often abbreviated as BPE, is conceptually simple. It begins with a vocabulary of individual characters. Then it repeatedly merges the most frequent adjacent pair of tokens into a new token. Over many iterations, common patterns become single tokens. For example, T and H might merge into TH, and later TH and E might merge into the. The algorithm greedily captures frequent substrings. This results in a compact vocabulary that balances coverage and efficiency. Word piece tokenization, used in some transformer models, is similar in spirit but differs in how merges are selected. Instead of purely frequency-based merging, it uses a likelihood-based objective to choose which subwords improve the language model's training objective. In practice, word piece tends to produce slightly different segmentations, often favoring linguistically meaningful fragments. The anagram language model tokenizer takes yet another approach. Instead of building tokens by merging upward, it starts with a large candidate vocabulary and removes tokens that contribute the least to modeling likelihood. It treats tokenization as a probabilistic segmentation problem. One interesting property is that it can naturally support multiple possible segmentations during training, which can improve robustness. Regardless of the algorithm, the end result is a fixed vocabulary of tokens. This vocabulary is one of the most consequential design decisions in a language model. It affects memory usage, inference speed, multilingual support, and even subtle behavioral quirks. One subtle but important aspect of tokenization is whitespace handling. Humans tend to ignore spaces as separate units of meaning, but tokenizers often treat them very carefully. Many tokenizers encode leading spaces as part of tokens. For example, the token for apple may be different from the token for apple with a leading space. This design helps the model learn word boundary patterns more efficiently, but it also creates surprising behavior when counting tokens or constructing prompts. Another critical concept is byte-level tokenization. Some modern systems operate not directly on Unicode characters but on raw UTF-8 bytes. This ensures that every possible input string can be represented without unknown tokens. It also simplifies multilingual handling. However, it can produce token boundaries that look strange to humans, because the tokenizer is operating at a lower abstraction level. When we talk about vocabulary size, most modern large language models use vocabularies in the range of about 30,000 to 100,000 tokens. This number is a compromise. A larger vocabulary reduces sequence length because more text fits into each token, but it increases the size of the embedding matrix and softmax layer, which raises memory and compute costs. A smaller vocabulary saves parameters but produces longer token sequences, which increases attention costs. Tokenizer design is therefore a systems engineering trade-off, not just a linguistic decision. Tokenization also directly affects context length. When a model is said to support, for example, 8,000 tokens of context, that is not the same as 8,000 words. In English prose, a rough rule of thumb is that one token corresponds to about 3/4 of a word, but this varies widely. Code, numbers, and non-English languages can have very different token densities. This is why prompts sometimes hit context limits sooner than expected. For highly technical audiences, it is important to understand that tokenization shapes the effective compression ratio of language into the model's attention window. If your tokenizer is inefficient for your domain, you are wasting expensive context capacity. This is one reason domain-specific tokenizers can outperform general-purpose ones in specialized applications such as bioinformatics or source code modeling.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.